And this is a joint work with Anne Broadbent at University of Ottawa. And this result is, it lies in the intersection of these three different fields: quantum information theory, cryptography, and theoretical computer science. So in order to slowly get into our result, I'll first try to define the basic notions of these topics before getting to the details. And in order to start that, I'd like to start with the notion of interactive proofs in theoretical computer science. So, a lot of you might know, like we can define problems by we can group problems in complexity classes to define its hardness. And the complexity class NP tries to model the problems that are easy, whose solution is easy to verify. So in order to be a bit more precise, we say that a problem is in NP if there exists a polynomial time algorithm that we call V, or the verifier, that receives some help, untrusted help from the prover, and decides to accept or reject. And here the idea is that the verifier wants to prove some statement, and for true statements, there is a proof that convinces the verifier that the statement is true. Or if the statement is false, no matter what the prover sends, then the verifier should reject, should check that this proof is wrong. And the concept of NP is a cornerstone in complexity theory. And given its importance, it was also extended to different settings that have had fruitful applications. And one of these extensions is the complexity class IP. And here we still want to prove truth or false, like to prove that statements are true, but now we're also given the power of interaction. So here the verifier communicates back and forth with the prover. And after this communication, this verifier should accept or reject. And again, we want for true statements, there exists some strategy for the prover. So there is a set of messages that the prover might send that makes this verifier to accept. And for strings for false statements, no matter what this prover does, this verifier should reject. And actually, this power of interaction gives a lot of computational power to this model, because we know that this is equivalent to all problems that can be solved in polynomial space. So we strongly believe that the given interaction to a proof system strictly increases its power. But then to cryptography, just interactive proof systems are not sufficient. So we require more properties from these proof systems. And one very useful property is what we call zero knowledge. So again, we assume that you have this interactive proof system, but now we want to prevent the verifier from learning secrets from the prover. So the idea is that at the end of the protocol, the verifier didn't learn anything. But this is a bit, this is the rough, definition. So in order to be more precise, we need to add more objects into this set. And and also as we want to hear that the verifier does not learn anything, we kind of think that this verifier is malicious. So we think that the verifier might behave dishonestly in order to try to learn as much as she can from the prover in order to gain information that she was not supposed to have. And we have that this polynomial time verifier should also output some, it interacts arbitrarily with the prover, and then outputs some object that has some distribution X. So with the output of this malicious verifier has some output, like it's a random variable. And in order to show that this protocol is zero knowledge, the formal definition is requiring the existence of simulator that is also polynomial time, but does not talk to the prover. And this polynomial time simulator also has output some random variable y. And in order to say that this protocol is zero knowledge, we want to say that y and x cannot be efficiently distinguished. Because if they cannot be distinguished, then the verifier could show up this value x that she has, but this could have actually been cooked up without talking to the prover. So that's something that does not require the secret that the prover has. And in order to formally define these, we require that any polynomial time algorithm, A, it cannot see the difference when it's given some X that's drawn from the first distribution, or if it's given some input Y that's drawn from the second distribution. So we want that whenever like this algorithm should behave exactly the same, regardless of or almost the same, regardless of these input distributions. And this notion has been, as I said, fundamental to the notion of, like it's a fundamental notion in modern cryptography. I don't know if there's any question, like if there are any questions now, but I have an example. So zero knowledge is usually something that it seems too powerful to be true. So I'd like to first give an example of zero knowledge protocol, and then maybe we can open for questions on this topic if there is any. And the canonical one of the canonical zero knowledge protocols is for the problem free coloring. And here the verifier has as an input some graph, and the verifier wants to know if there is a way of coloring this graph with only 3 colors in a way that every edge only touches two nodes with different colors. And let's try to have an interactive rule system for that. So the prover is unbounded, so it's very powerful and can iterate over all the colorings and find if there is any coloring that satisfies this property. And the prover could just, for instance, just send this coloring to the verifier, and the verifier could check if all the colors have the correct property, like two nodes with that are adjacent, they don't have the same color. This protocol is complete, meaning that if the graph is 3-colorable, the prover can convince the verifier. It is sound because if the graph is not 3-colorable, if there's no such coloring, no matter what the prover sends, the verifier can check if this graph is 3-colorable or not. But this protocol is far from being zero knowledge because the verifier is learning the coloring, and this is not something that we expected to be done efficiently by this verifier. So we have to propose, we have to change a bit the protocol. And for the protocol, so instead of the prover sending this coloring to the verifier, the prover will just permute the colors, and this is more of a technicality. But then this prover will put each color into a safe, and we'll send each of the safes to the verifier, but we'll keep the code to open them. So the idea is that, okay, the prover writes on a piece of paper and you can imagine it as this. The prover writes on a piece of paper and sends all the safes to the verifier. The verifier then picks one of the edges informally at random and asks the prover, give me the code to open the safe, the corresponding safes of this, for instance, of this edge. And the prover then sends, okay, I'll give you the codes that open both safes. And then the verifier just opens it and checks if the 2 colors are different. In cryptography, this safe is what we call bit commitment, but for this talk, like during this talk, I'll keep this with this analogy of safes for simplicity. And now this protocol is complete because, again, if the graph is 3-colorable and the prover behaves honestly, then the verifier always see 2 nodes that have a different color. The protocol is sound because if the prover sends a coloring and the verifier opens one of these red uniformly at random, then with probability, with no negative probability, this verifier will open the boxes that contain the same color because there's no way that they all have different colors. And now, more importantly, this protocol is zero knowledge. And I won't prove this formally, but the intuition is that everything that's in the safe is not known by the verifier. And the only thing that the verifier knows is that when he opens the 2 safes, he sees 2 different colors. So we could simulate this this distribution by putting an arbitrary color in each safe, and then just coloring this one edge with 2 different random colors. So this is very rough and maybe too fast, but this is the intuition why why this protocol is zero knowledge. And then we, since through coloring is an NP complete problem, we now have a zero knowledge for all problems in NP. So yeah, I don't know if there is a question now.
There is no questions, but there is a comment from Gilles Brassard. He says that for those who might not know, it would be useful to say that the indistinguishability of X and Y only has to hold on yes instances.
Oh yeah, that's a very important. Thanks, Gilles. Yeah, the zero knowledge property only holds when there is some secret to be hidden. So, for instance, if the graph is not through colorable, then we don't care about anything. We just care when there is a through coloring that to be hidden from the verifier. So this protocol is completely classical, but we're in QCrypt, so we have to go to quantum. So now we go to since all of these proof systems, they have been very important in classical cryptography and computer science, we also have defined the quantum version of them. And in particular, we have the quantum version of NP that we call QMA. And here we have a quantum proof system where this verifier, that's a polynomial time quantum algorithm, receives from this quantum prover a quantum proof that will help him to verify if a problem is in the language or not, or if it's a yes instance or no instance, or as I said before, if the statement is true or false. And again, we want that for true statements, there is this quantum state that the prover will send to the verifier that will make this quantum algorithm to accept with high probability. Or for false statements, no matter which quantum state this prover sends, this verifier should reject with high probability. And again, with we can add interaction into these proof systems, and now we can define the complexity class QIP, where the verifier and the prover they can send quantum state back and forth, and at the end of the day, the verifier should accept or reject, and the acceptance and rejection probability is what we expect it to be, extending the previous results. We also have the QIP is equal P space, so this we also expect this complexity class to be much more powerful than just a single shot quantum proof. But again, for cryptography, this might not be sufficient, when we also might require other properties such as quantum zero knowledge. So now we can extend this notion also to in the quantum setting. And as before, the verifier is a quantum algorithm, but now this verifier could be malicious and try to deviate from the protocol to learn as much as she can from the prover. So she might, so that's why we assume that it could be malicious. And then at the end of talking, after talking to the prover, this verifier outputs some quantum state row. Now we don't need to have, okay, the probability distribution, the random variable is somehow in the mixture of this quantum state row. And as in the classical setting, what we want now is to have a simulator that might depend, of course, in this malicious verifier. And this simulator, again, does not the prover, but outputs some quantums, is a quantum algorithm that outputs some quantum state sigma. And the quantum zero knowledge protocol means that for yes instance, so for true statements, rho and sigma, they cannot be distinguished. And this again means that for any polynomial time quantum algorithm, this polynomial algorithm should behave almost the same if she was given the reduced the density matrix rho or the density matrix sigma. So now let me describe a bit the landscape in zero knowledge for quantum proof systems, or for QMA, and the complexity class that I defined. And using a lot of complexity theoretical results, we already knew that there exists a quantum zero knowledge protocol for QMA. But this protocol is very inefficient, like from the perspective of the prover, and it is complicated. And actually, we don't have using these complexity classes inclusions, we lose all the intuition about this protocol, and we actually, I think, we don't have it written down. It's something that is just a matter of complexity classes. It's just a theoretical result. Until in 2016, Broadbent G, Song, and Watrous, they finally show a protocol for a zero-knowledge protocol for QMA, for quantum proofs, which is much more intuitive. So it uses the structure of this QMA proof system, and in particular, they have a protocol that if the prover of the zero-knowledge protocol is given the QMA proof or the QMA witness, then the prover only needs to run, the honest prover only needs to run in polynomial time. And that's a very desirable property for cryptography. But again, this protocol, okay, it's much better than this previous more complex one, but still it's not as simple as the zero knowledge protocol through coloring that I show. So it needs much more crypto, it needs more complication, more rounds. So it's not what to expect from the nice textbook protocol for zero knowledge for QMA. And then finally, last year with Broadbent, we explored some technical tools that were developed in my result with Sloths and UN. And we finally show a very simple protocol for QMA. And this is the same style of protocol as the one for through coloring. So it's the one that the prover commits to some information, the verifier performs a random challenge, and then the prover answer or open some of the commitments that were done in the first round. We also have some variations of this result. Because of the time limits, I won't discuss much about them. But also an interesting thing is that we have other applications that are also for complexity theory, and actually some of these applications are the ones that enable us to have these zero knowledge protocols. And in particular, we finally show the QMA hardness of a problem called the consistency of local density matrices. I'll define this problem more precisely in the next slide. But this problem was open, it was not known if this problem was QMA hard since Ika Liu defined it in 2006, I think. And for the rest of this talk, I'll give a bit more details on this problem, on consistent local density matrices, and how we can have simple zero knowledge protocols from it. And then I'll give some ideas that allow us to prove the QMA hardness of this problem. But and it's not just because this is not just for complexity theory. These ideas, they might be useful somewhere else. I think this is a tool that could have other applications. So if there's no question, I will switch gears and start talking about consistent local density matrices.
Yes, no questions at the moment.
Okay, thanks. And this problem is the following. So imagine that someone gives you a lot of pieces of quantum state. So someone gives you a lot of local density matrices on, let's say, 6 qubits. So you have the density matrix rho 1, rho 2, up to rho m, and they might intersect, they do intersect actually. And then you want to know if there is a global quantum state that here are called psi. So if there is this global quantum state, whose marginals are consistent with all of these local density matrices. So more formally, we ask is there this this global quantum state psi, such that all these reduced density matrix, the matrices are close to the rho i's, like the inputs that you had, up to some negligible epsilon. Or on the other hand, if no matter which quantum state you have psi, there must exist one of these density matrices such that the reduced matrix of psi on the corresponding qubits is very far from the density matrix on 6 qubits that you had before. So there is an inverse poly gap between this distance is at least an inverse polynomial. As I said, in 2006, Liu defined this problem, and it proved that this problem is in QMA. So it shows that one can prove that there is a quantum state that allows us to check if the margins are consistent. And this containment is actually somewhat simple. So the quantum proof is the most natural one that you can think. The quantum proof is just the quantum state that is consistent with all the local margin or with all the local marginals. It's not as simple because actually you have to give a lot of copies of this quantum state psi. So the proof is, let's say, a lot of copies of psi. And in order to verify that the marginals are consistent, one can use some sort of tomography. So you can do tomography on the local parts of these copies of psi and check if it is consistent with the rho wise. So there are some technicalities that are not in order to this proof system to work, you have to deal with some technicalities, but I don't want to talk about this now. Like I assume that, for instance, all the copies are intentional product and so on.
Alex, sorry to interrupt you. Just a quick question on this slide from Gilles Brassard. Which norm are you using to compare density matrices?
The trace norm. So Liu proved that this problem is in QMA, and he had some partial results to prove that this problem is actually QMA hard. So it encompasses all problems in QMA. Also, or on the other hand, you can use this problem to describe all problems in QMA. But as I said, since then it was an open problem to fully prove that it's QMA hard. And as I said, with broadband, we finally showed that this problem is QMA hard. And this is very important because now it allows us to, for instance, give a zero knowledge protocol for this problem. And once you do that, you have a zero knowledge for all problems in QMA, because now this problem is a good representative of this complexity class. And before explaining how we prove this QMA hardness, I'll first show like the protocol. The zero knowledge protocol is actually very simple once you have this result. And I'll next now I'll explain how the zero knowledge works, or how the zero knowledge protocol works. And here, as I said, the input that the verifier has is this description of this local density matrix rho 1 up to rho m. And as I said, in the original QMA verification, the prover is supposed to have a lot of copies of the state that's consistent with this local density matrix. And the protocol works as follows. The prover applies a quantum one-time pad on this state and keeps all the one-time pad keys. And if you don't know what the one-time pad key is, you just apply random Paulis, and you keep the Paulis, like you keep returning the Paulis. And the point is, if you only have the first state, you have the total mixed state, and you have no information about what's encrypted. And now we need to use a bit of cryptography. So as in the original, like in the zero knowledge protocol for three coloring, the prover will put each of these one-time pad keys in the safes and send everything. So sends the state and all of the safes to the verifier, but again, keep the codes, the code, like, or the password to open the safes. And since the verifier cannot see what the code is cannot see what the one-time keys are, because they are because of the property of the safe, you cannot see inside the safe. Then this quantum state is totally unknown to the verifier. So it's the totally mixed state, and the verifier has zero information about it. Then in this protocol, the verifier just says, okay, I want to check if the state that you sent me is consistent with the ith density matrix. And then the prover gives the codes that open the safes that reveal the one-typed keys for the qubits corresponding to the density matrix ROI. Once the verifier has this information, has those one-time-pad keys, the verifier can undo the one-time pad, and then she's supposed to have the raw qubits, like the raw qubits of psi on the corresponding qubits of the density matrix ROI. And once she has removed this one-time pad, she can run the same verification that she did in the original QMA protocol. So from the properties of the QMA protocol, we have that this protocol is complete and sound, and also about properties of the safes or in cryptography bit commitments. But also now the thing that we're gaining is that this protocol is now zero knowledge. Why? Because the only thing that is outside of the safe, so everything that the only part that the verifier knows about this quantum state is the qubits corresponding to the density matrix ROI. But the verifier, if again, this only works for yeses, so it only works when there is a state that's consistent of these local density matrices. But if this is the case, the only qubits that the verifier has on the clear without the one-time pad key are completely known by them, because he had the description of the states, like he had the classical description for ROI. So the intuition here is that the verifier is not learning anything about this state psi, because he knew the marginals already. And of course, the problem is how they connect to each other, and this is still not known after the verifier runs this protocol. And then this is just the intuition level. So we can formalize it and provide a simulator whose view will be indistinguishable from the view of the verifier in this protocol. Now I'll tell a bit how we can prove that this problem is indeed QMA, the consists of local density matrices is indeed QMA hard. And the idea is to use error correcting codes. So for instance, let me explain or define things by example. So imagine that you have the Steane code. So the Steane code maps the qubit 0 and this logical qubit 0 into this physical qubit here, or physical state here, and this qubit 1 here to this physical state here. And if you have some quantum state psi, and you consider the encoding of the psi, so we have 7 qubits that encode this logical 1 qubit psi. We can do by inspection that if someone asks you, like gives you 2 positions of this code word, so gives you asks you what's the reduced matrix of this code word on these 2 qubits, you can compute it very easily without seeing psi, because by inspection, for every reduced density matrix on 2 qubits of the Steane code, you have the total mixed state. So in particular, there is a very efficient algorithm that gives you I and J and computes the trace of this encoding of any quantum state psi or any qubit psi on the qubits I and J, because this algorithm just output identity. But unfortunately, this is not, okay, things are not, these are good, but not great for now, because if someone gives you 3 qubits, then one cannot compute these density matrices efficiently. And one can see that, for instance, even for 0 and 1, this depends on the qubit being encoded. And the idea is that, okay, because 3 is bigger than the distance of the code. So this is, okay, this is the technical problem that we have here. But then when in this work with Lofstra and Nguyen, we define this notion of as locally simulatable codes. And what we show is that the Steane codes are as locally simulatable. So, and the idea here is that you want to do the same thing that we did with the normal Steane code. So we want to simulate density matrices of code words, but now for a bigger number of qubits. And what to show that if you fix an S and you pick a big enough concatenation of the Steane code, then first you can compute the density matrix on any set of S qubits of an encoding of some state row encoded under this error correcting code. So the same thing as discussed before. But we have also something stronger. We can show that you can compute the density matrix of the snapshot of computation on these code words. So also explaining by example. So imagine that you have the encoding of some qubit row. And we have, for instance, for the properties of the Steane code that you can apply Hadamard's transversally. And what we show is that for every snapshot, so for every snapshot of the computation, we can also compute the reduced density matrix, the S reduced density matrix of this snapshot. Okay, so this is this simulatable codes notion that we use in order to prove this QMA hardness. And let me now also describe in more details how we prove hardness. And one of the second key idea is to use this the famous circuit to Hamiltonian construction by Feynman or Kitaev, depends how you see it. And the idea is that from this circuit to Hamiltonian construction is that when you can start with a quantum circuit, let's say that that is decomposed, let's say in gates U1 up to UT, where each gate is, let's say, 2 local. So you have 2 qubit gates. Then you can define some Hamiltonian HV. And if you don't know what a Hamiltonian is, it's not so important, but the idea is that this Hamiltonian fixes some state that we call the history state. And this is the state that contains a superposition for every snapshot of the computation on V. So, or in other words, so you have the superposition of every time step from 0 to t, and you have some clock register that tells, okay, this is the snapshot at time t, and this is a stage of the computation at the tth step. So the idea is that this Hamiltonian, that like this object that you construct, will somehow pinpoint this state that you call the history state. And the acceptance probability of this verification circuit is related of how good this history state will be in respect to this local Hamiltonian. And the idea that we have in order to prove this QMA hardness of consistent of local density matrix is now tweak a little bit this verification circuit in a way that when you consider the history state of this new verification circuit, this new verification circuit is simulatable. So one can efficiently compute the reduced matrix of this new verification circuit, and this is the then this would be this consistence of local density matrix instance that would be corresponding to this QMA verification. So let me give you a bit more of details. So when you start with this QMA verification V, again, it is decomposed on these gates and has this quantum proof sign it. In this, we now want to construct a new quantum QMA verification system, V prime, that instead of receiving this initial state sign it receives a more complicated one. It will receive the one-time pad of this circuit, along with the one-time pad keys. And again, like this one-time pad keys and the one-time pad inside this here is a bit for technical reasons. But the important part here is that everything here is encoded under a simulatable code. Then this new verification V prime will do some extra steps. So for instance, check if the encoding of every qubit here is correct. We'll, under this encoding, undo this error correcting code. create encoded the auxiliary bits, and then perform the original verification here, but on this encoded state, either by doing transversal gates or by doing, let's say, T-gadgets. So we borrow from these techniques from fault-tolerant quantum computation in order to do universal quantum computation inside this encoded state. After doing this, the verifier has the encoded output, and then the verifier can just decode it and decide to accept or reject. So what we're able to, so then in this work with N, what we're able to show, there exists a classical algorithm that can compute in polynomial time the description of all reduced matrices of the history state of this new V prime. And this algorithm cannot, of course, this polynomial time algorithm cannot decide the QMA, so it works for both yes and no instances. But what we're able to show is if there is, once you compute these local density matrices, there exists a global state that's consistent with them, if and only if it was a yes instance for the QMA problem. So I think I'm a bit out of time, right?
Yes, it would be nice if you could wrap it up.
Okay, so I'll skip a little bit the sketch proof, and I'll leave it for the questions. Another thing that I'd like to highlight is that in this work and in a concurrent work with Michelangelo, Vidic, and Zhang, we also define the notion of proof of knowledge. Is that this is a notion that tells that not only the prover has it's a protocol that not only makes the verifier accept or reject, but it also, if the verifier accepts, she knows that the prover indeed has the secret, so indeed has the quantum witness. But I'll also leave this for the questions. And I'll just want to finish with some interesting opening questions, of course, in my point of view. So one embarrassing question that I've been asking a lot, maybe I should try harder to solve it. So we know that classically, zero knowledge is very influential and very useful in different settings. And we don't have too many applications for quantum zero knowledge. So can you use these quantum zero knowledge protocols to build other quantum primitives? So it's some primitives in quantum cryptography. An interesting question is that we know zero knowledge works well in the quantum setting, but how about in the no signaling setting? So do you have that non-signaling interactive real systems? They are also closed under zero knowledge. And then we'll have more technical questions that I think I'll leave for now, and thank you for your attention.
Thanks a lot for your very nice talk, Alex. So now we have some time for questions. At the moment, we don't have any questions in Q&A. So, okay, we have one. Question by Gel Don. In your ZK protocol for the consistent local density matrix problem, the prover might hold only a single copy of the witness state, and it has to send this state, encrypted with a one-time pad, over to the verifier. Does this mean that it can only run a single execution of the protocol? Do you consider this a weakness of the protocol?
Yes, it is. I think it's a weakness. I'm not sure if it's a weakness of the protocol or of the setting. So the question is, you're completely right. So we cannot reuse these quantum states. But maybe one thing that one could try to show is that this is inevitable. And this could indeed be the case, right? Because even for QMA, you also have this same type of argument, right? So if the prover only holds one copy of the QMA witness, and when this prover sends it to the verifier, then the prover, it has to find again this same quantum state. So it's not easy to copy, right? So we don't expect that quantum proofs can be easily copied. So it is a weakness of my, so just to wrap up. So I think it is a weakness of my protocol, but it could be just a weakness of the model.
But that's still an open problem.
That's an open problem. Yeah. So this is an open problem if this is inevitable.
I mean, it could even be useful in some settings, right? To be restricted to only proving once.
Exactly. So when you use non-clonability of proofs to do something, yeah.
Yes, thank you.
Thank you. So there is another question from Christian Schaffner. Do you want to ask it yourself?
Yes. So I was just wondering, when you define the simulator, I mean, it's clear to me that it works for honest verifiers, but do you run into any issues if you consider dishonest verifiers?
No. It works for dishonest. So if you're used to zero knowledge in the classical setting, then we don't talk about transcripts. It's just about like the malicious verifier interacts with the prover and then outputs some quantum state. And the idea is that the simulator is able to run. Okay, the idea is that the simulator is able to run this verifier, this dishonest verifier in a black box, and outputs another quantum state sigma. And then what we want to show is that for every polynomial time malicious verifier, these two quantum states are close, or sorry, are indistinguishable.
Right. Yeah. Okay. And the simulator just does the same as the dishonest verifier would do, basically.
Yeah. No. Yeah, it tests. Yeah, it somehow uses. Yeah, whenever the verifier has to do some computation, he asks this in a black box to this malicious verifier to run it. Yeah.
Okay, is there any more questions?
Yeah, I'd like to follow up on the simulator question, because even for an honest verifier, it's not fully clear to me why it is zero knowledge. But sort of the intuition is that the state that he gets, sort of the part of the state that gets decrypted, is sort of the state that is anyway described by one of these row i's. Right, that's the intuition.
So okay, I can okay.
But sort of my question,
I'll give you the simulator for the honest case.
Is efficiently producible, given the description.
Yeah, because because it's a 6x6 matrix, so you can do that. Like the point is this qubit, like this reduced matrix has constant size.
Oh, okay.
And then it can be efficiently computed.
Okay, yeah, makes sense. Thank you.
Okay. Thank you very much, Alex.